Welcome once again to RF transceiver design course. We are discussing about active devices. In last two lecture we have seen various technologies that are used for RF or wireless application. Device technology we have seen. We have just given the brief analysis and we are discussing about the MOSFET. We have started discussion on the large signal analysis, and now we will see that what are the capacitance. We have just stopped at capacitance. We are identifying the various capacitance associated with the MOS transistors. So, we will see more in detail. So, in last class we have seen that there is a P substrate channel to bulk capacitance CCB, then CJSB, that is a junction capacitance, CJDB, source to bulk and drain to bulk, and we junction capacitance is given by oxide capacitance, the width of the MOSFET and effective length L effective, which is because of the gate overlap, that is a L minus 2 LD, and the overlap capacitance C overlap, which is because of the overlap, that is a LD. So, WLD C ox. So, L effective we can write it as a L minus 2 LD, and C ox is epsilon ox by T ox, and overlap capacitance is WLD C ox. Then there is a CCB, that is given by epsilon silicon by XT into WL effective, where epsilon silicon is epsilon of silicon and XT is given by 2 epsilon Si by Q into N substrate. Then there is a potential difference 5S minus Fermi potential difference 5F. So, this is a XT. Based on this we can get all the capacitance. Now, we will try to see that how we can get the different capacitance when your MOSFET is in different region of operation. So, if we make a chart, here there is a capacitor, then when MOSFET is off, then when it is in triode and in the saturation. So, if we try to find out the capacitor in each region, so the CGS, which is between gate to source, what is the capacitor? So, because it is off, there is only overlap capacitor that we can see. So, mostly overlap capacitance will be dominated COV. Then in triode region, because of the channel has been formed, there is a C overlap plus CGC by 2, that capacitance will be added, and CGC is given by C ox WL effective. And when it is in saturation, there is a same overlap capacitance plus 2/3 of CGC. So, how this 2/3 came? Because when there is a during the saturation, if we try to draw here the channel, this is N plus, and in channel there is a pinch off will occur, and due to that pinch off, the more electrons are there at the source side and less electron will be there at the drain side. So, the if we see that 2/3 of the electrons are at the source side, and that is causing the 2/3 CGC. Because of that, in saturation region you have a more CGS. Then CGD, gate to drain, same C overlap, So, in triode region there is a weak inversion, and it will be the channel will be the uniform. So, average has been taken. So, half of the capacitance will be considered on the source side and half of the capacitor has been considered on the drain side. So, that is why this is a C overlap plus CGC by 2. So, half will be on the source side and half will be on the drain side, and mostly the in saturation 2/3 CGC, the remaining part will come, but it is a negligible. So, only overlap capacitor will be there in the CGD. Then there is a CSB, source to bulk. So, in source to bulk there is a CJSB that will dominate, and when there is a triode the same capacitance will come CJSB plus C, then CCB, that is channel to bulk capacitor by 2. And in saturation there is again there is high capacitor, that is a C overlap CJSB, which will be constant, plus 2/3 of CCB. So, another capacitance, that is a C drain to bulk, it is a CJDB plus in triode region same capacitor CCB by 2, CB by 2, and in saturation in drain there is a same CJDB that will come. And this junction capacitance, it is a well known capacitance. I will just write a basic equation of junction capacitance. If you are interested more in detail about understanding how this all equation and capacitance are coming, you can refer any semiconductor device book, or you can refer to the lecture on semiconductor devices. So, this is a 1 plus reverse bias voltage VR, built in potential B, psi B, then there is a empirical constant M. So, that will change with vary with the process. So, this capacitance you can find out the CJSB, CJDB. So, overall the capacitance there is a CGS which will dominate, and that is depend upon CGC and overlap capacitance. So, if you try to draw in terms of the schematic, this is a CGS, then CGD. So, from gain to drain, drain to bulk. So, all these capacitance we have seen, and that will contribute to the in RF capacitance are important to consider. So, we will see the why capacitance is important in RF, that by when we are discussing the FT of the transistor. So, frequency response of MOSFET. So, if we consider a single device, and if we want to find out that what is the maximum frequency that I can use the device. So, these FT and fmax are very important parameter that will tell us that up to what extent we can use our device considering the RF frequency. So, FT is nothing but transition frequency when your current gain is equal to 1. We will try to derive the FT and fmax both. So, FT is given by, so if we define FT, it is a transition frequency at which current gain is equal to 1. So, at this frequency you can no longer consider the transistor as a amplifier device, because whatever is the input current, same output current you will get. There is no amplification will be involved. So, if we want to derive for the MOSFET, so FT, so this is a NMOS, then there is a input current I in and output current I out. So, we will try to find the derive the FT. So, in order to derive the FT, there is a CGS capacitor, CGD capacitor, because this because of CGS the current gain is going to 1. So, there is a effect plus or minus VGS voltage, GM into VGS is a drain current, then there is a this is output current IO. So, and this is a I in. So, generally it is denoted as a small signal. So, it is better to write a small letter. So, if you write IO, which is equal to GM into VGS, and the VGS is given by S CGS plus CGD into V, or here your I out is this and your I in. So, I in is equal to S VGS CGS plus CGD. So, if you try to keep this V in this, then you will get I out, means that is, if you try to keep VGS value, then GM then I in divided by S CGS plus CGD. So, your output by input current is given by GM S CGS CGD. If we replace S with J omega, GM divided by J omega CGS plus CGD. So, the what is the derivation, means what is the definition of FT? It is a transition frequency at which current gain is equal to 1. So, I out is equal to I in. So, in this equation, if we put I out is equal to I in is equal to 1, I out divided by I in is equal to 1, then that is the FT, which is given by 1 into GM J omega T, that is CGS plus CGD. So, your omega T is given by, because here this gain absolute gain is 1. So, we can take a mode of this. So, omega T is given by GM by CGS plus CGD. If we write in terms of FT, that is 1 by GM by 2 pi CGS plus CGD. So, this is a transition frequency, and FT is depend upon transconductance GM and the gate to source capacitance CGS and gate to drain capacitance CGD. So, in many cases the CGD is negligible, So, if CGD is negligible, we can also write FT. So, FT can be written as Gm by 2 pi CGS plus CGD. If CGD is lower than CGS, we can write FT Gm by 2 pi CGS. So, this is a basic equation of the FT. This both can be considered, and if I write down omega t in this equation. So, another equation, current gain AI, which is equal to FT by JF, that can also be written, omega t by JF. So, this is a equation of FT. So, FT will tell us that what is the maximum operating frequency at which we can work. Another important parameter for any devices, that is a fmax. So, we will try to derive fmax also. So, in order to derive the fmax, what is the definition? So, fmax, it is a maximum frequency at which power gain is equal to 1. So, when, because in power is important in high frequencies, and in the previous what we have seen, we have just considered the small signal current gain, which is equal to 1. However, in fmax we will consider the power gain where the power is equal to 1, and whenever there is a power will come into the picture, we should know the what is the input impedance and output impedance of MOSFET. So, we will try to derive the input impedance. So, when we derive the input impedance, we also need to consider the RG. So, this is if we, there is a RG, then this is CGS capacitor. So, there is a voltage drop VGS, then CGD capacitor, and this is a current GM into VGS, this is RO, output impedance. So, when we want to find the output impedance, we will give the test voltage and find the test current, and this is connected to the ground. We can get, this is a test voltage Vt and test current It. So, now we will find the relation between Vt and It. So, your output impedance Z out is equal to Vt by It. So, now It can be given as a Vt by Ro plus the current Gm into VGS current and current into the CGD, that is IDG. So, this IDG is generally very small compared to Gm into VGS. So, we will mostly consider Vt by Ro plus Gm into VGS, and then what is the Vt can also be written as a VGS. VGS can also be written in terms of VT. So, VGS which is equal to CGD by CGS plus CGD into VT. So, if we put this VT in this equation, so VT we can write VGS in this equation, we will get IT which is equal to VT plus GM into CGD by CGS plus CGD into VT, and this is VT by RO. We have already derived one term GM CGS plus CGD, that is FT. So, we can write IT which is equal to VT by RO plus F omega t. So, this is omega t into C GD VT. Then your VT by IT, which is the output impedance, is nothing but 1 by RO plus FT omega t. So, only the difference is omega t or FT we can consider, that is 1 by 2 pi FT. So, omega t into CGD. So, this is the output impedance, that is a Z out. Now, we can also get the input impedance, that is a straightforward, that is RG plus 1 by j omega CGS, but this j omega CGS is much low at the high frequency. So, the mostly it will be considered the RG. So, this is the input impedance and output impedance we have find out in order to find the input power and the output power. Now, we will derive the input power and output power. So, the power when we are considering the output, so if you have connected the same impedance in order to have the maximum power transfer, so your RL which is equal to R out. So, in that case your current flowing through the IO output current is a half of the current which is coming from the MOSFET, that is half current. Similarly, at the input side you have ZS which is equal to RS, then your input current I in is half due to the Vs by 2 Rg. So, here what we have considered, there is a Zs and there is a source Vs and there is Rg, that is a input. So, this is the input side, and at the output you have a Gm into Vgs, then your Z R out and your RL. So, your input current is given by IOS by 2 and your output current is given by IOS by 2, your input current is given by Vs by 2 Rg. Now, we try to find the power gain, that is a Gp. So, Gp is given by 1 half IO square into R out divided by 1 half I in square into R in. So, this we already find out. So, we can write 1 by 4 I O by I in whole square, and you have a R out which is R L. R out is equal to R L, R in is equal to R G. So, and we already have derived that this I out by I in we can also write F T by F, that is whole square R L into R G. So, here this power gain we should just put the R L and R G. So, your Z out is this and your Z in is R G. So, now we put the Z out. So, you will get the your RL is equal to Z out is equal to 1 by 1 RO plus omega t into C G D. So, if I will write in terms of Ft, 1 by RO 2 pi Ft into C G D. If we keep in this equation, we will get fmax. So, RL we put in this equation, we will get fmax which is equal to 1 half square root of, it is 1 half Ft divided by square root of 2 pi Ft Cg d into Rg plus Rg by Ro, because we have taken this Rg inside the this term. So, Rg is multiplied and then this is Rg by Ro. So, this is a fmax equation, and which is also depend upon the Ft of the transistor, and based on the Ft we, and while finding out the power gain, generally input and output is a match, and at that point we get the current gain, output current gain divided by the output power divided by the input power, and we have derived the this is output power, input power. So, then we have considered the output impedance and input impedance, whatever we have find out we kept in this equation. So, this is a final equation which is a function of Ft by Fmax. So, this generally when any device is given, the Ft Fmax is written like Ft and Fmax. So, both are mentioned together so that you will get the power gain, means how your device will work when there is a power is involved and when there is a small signal current gain is involved. So, Ft Fmax are the very important uh, parameters of any devices, and if you know the Ft or Fmax, you can easily work out that what will be the frequency at which your device will work. And if you are targeting for very high frequency design, then let us say millimeter wave or sub terahertz, you should consider very high Ft Fmax devices. We will discuss more about device. So, we have discussed Ft Fmax of MOSFET. We will also derive the same for the BJT as well. Thank you. We will discuss about the BJT in the next class.